the event's frame of reference. This will help us now locate ourselves. Now, since these lines, as we said some time ago, do not really represent the time, this is just to help us. These lines represent displacement, and we know that any displacement will be equal to speed times time, or velocity times time, vt. So for the observer in the event's frame of reference, the distance will be given by speed of light times time. In this case, time, proper time t naught. Now for the train is moving at a velocity known or unknown, but now in time t is called the dilated time. Now, what is the time taken by the photon? It's the same time as time t, but we know that the velocity of light is c. So you can see that we have this result. If we are to express in terms of to express the distances in terms of this, we can then be led to express the value of ct using the Pythagorean theorem, where we know that the hypotenuse, all of this squared, should be equal to the opposite, all of it squared, plus the adjacent component, all of it squared. So now this is a very important formula that can help us to find out the relationship between this time measured outside the frame of the event outside the frame of reference of the event, and then compare the proper time measured within the frame of reference of event. So now here we will do some algebra, of course, and try to figure out the relationship. So what can we do here? Let's express, we know that this is the hypotenuse, so basically we can remove the squares. If we express, let's put the proper time on one side of the equation. So if we bring the proper time on this side, or we leave it where it is, it will continue being positive, and then we will figure out that ct, this minus this, will give us this, and then we will continue to divide everything so that we can just remove common factors. At this moment, we will recognize that this is c plus t naught c squared, not t naught squared, will be equal to, here we can remove the common factors, that is t. We can do it at this moment. Let's see what happens if we remove t. We will be left with the speed of light, and now this is t squared, mind you. This is c squared minus v squared, and then t squared has gone out squared. At this moment we can actually bring the times together. Let's do it. We divide both sides by t squared, obviously, t squared, which leads us to, which can lead us here. Let's use space very wisely. So we'll have c squared. No, we wanted to, yeah, we have c squared and t naught, and then we will have t squared. This will give us c squared minus v squared. So let's put let's remove c squared from this side by dividing both sides by c, like this. So if we divide this by c squared, we're also obliged to divide this by c squared and divide this by c squared. What we do on the left, we do on the right. As a result, this cancels out, and then we have t naught squared over t squared will be equal to, so c squared over c squared will be equal to 1 minus v squared over c squared. So from here we could find the square root of these both. So if we find the square root of everything, we will have here that T naught over T equals this expression, 1 over C2. So this establishes a relationship. This portion of the equation, this here, is known as Lorentz factor, very important, represented by the Greek letter gamma. So Lorentz factor will be equal to 1, will be equal to, so here is actually 1 over this. This is the Lorentz factor, 1 over this expression. It's important because it can relate the time, dilated time. So the dilated time in this case will be given by, here we can multiply both sides by t and bring t here, which will give us a T naught is equal to T times this value times the Lorentz factor, and therefore the dilated time will be equal to T naught divided by the Lorentz factor, or since gamma is 1 over this, it will be equal to gamma times T naught. So T dilated time, and it will appear to be longer. The dilated time will be longer, as the word tells us, dilated. It will be longer than the proper time. And this is important in special relativity. And as we will see, gamma, Lorentz factor, is also used for length contraction, which is the opposite of time dilation, but for space. So as time is perceived to be longer for the one observing someone moving close to the speed of light, the opposite happens to length, to space. But we will see that in another video.